Hello guys, welcome back to my channel. It's been a couple of weird, messed up weeks. Many of you might be in disbelief when I started uploading some gaming videos on my channel, but I was really trying to expand a little bit and also trying to... Gaming is therapeutic, let me just put it out straight. It really helped me. Now, since we're all back here, and thanks for believing me that I will be back, and I am. So I did not disappoint you. Let's get started with the motivation for Laplace transforms. We know what Fourier transforms are. If you don't, just watch the videos before. Now we're just going to modify the Fourier transform slightly in via the motivation for constructing something like the Laplace transform, and then we're going to work more from there. So let's get started.
Hey guys, you're watching Gamma.
Okay, so before we do anything, let me just do a simple example here. Let's see, and that's some horrible drawing right there. Yeah, let me just do this more systematically. So assuming we have, okay, I'm not really used to this, bear with me. So assuming we have a function like this, it sort of is 1 when the x value is 0 and then drops off. So the function f of x, all my settings are kind of in a disarray here, is 0 when x is negative, and is e to the negative alpha x when x is positive. That's why we're getting this decay nature here, and there's 0. It really vanishes on the negative bit. Okay, so say we have to take the Fourier transform of this. It's pretty simple, the Fourier transform. It can be complex, that's what I want to emphasize. So it's 1 over square root of 2 pi, the integral negative infinity to infinity dx e to the negative ikx, where k is real. So I'm just pointing that out first. K is real. Well, the transform itself could be imaginary, and I will underline the things that are imaginary usually. Well, we know this exists because the integrand, it clearly exists. It's dying down at infinity, and at negative infinity part it's 0. So we don't really need to worry that much about the convergence of this thing. Convergence will become an issue later. So let's just split this sum from 0 to infinity, because the rest of it is just 0. Dx e to the negative ikx e to the negative alpha x, and this just evaluates the negative I over square root 2 pi times 1 over k minus I alpha. This is just simple integration here. Now if we want to invert this, so we want to regenerate our f of x from this Fourier transform, so we just invert the transform with the formulas that we established in the past couple of videos. I mean before the gaming ones at least. So I've this and f of k, which is complex. Here it definitely is with the negative I. So I'm just writing stuff out. I'm just being a little slow here. I don't want to rush into it. Just literally just substitute everything in. Oh, fine. Well, notice the problem, not really the problem here, is that we have to sort of expand our integration now, because we have this weird factor in the denominator and a k dependence in the numerator as well. So how will we do this? Well, what we can do is we can use our complex analysis, our contour integration. So let's say we have a contour, which I will denote with a curly f for the Fourier contour. It's literally everything that's the same. I'm collecting the square root 2 pi like this. See, I have dk because we're integrating over that way. Where k is complex, but only for this integration. Divided by k minus I alpha. And why is this useful? Because if you remember what we used to do before, is that we had a contour defined. And again, my drawing is becoming more and more horrible. Yeah, it doesn't matter. The procedure is more important than the diagram. So our contour was like this. From r to negative r, and then you took the limit as r went to infinity. That's just classic contour integration. There's an entire playlist about this. We talked about this in a complex analysis part before. And we have a pole at I alpha here. So here is what a contour looks like, but the problem is we don't know what x or what the entire contribution of the numerator is. We want this semicircular part to decay, and notice that will only decay when x is greater than 0. Because if you remember what we used to do, k is going to be r e to the I theta on the top bits. And we want to use our Jordan's lemma on top. We have this. We're going to have something like this on top. So if x is positive, that's when this top term will decay on the semicircle. If you don't understand what I'm talking about, just watch the previous videos. You'll piece it together. So this is the real axis, the imaginary axis. We're going to integrate this entire thing here. Is the Fourier contour. The top bit, the closure on top is for x positive. I can close it down as well, like this for a negative x, because I want because then r will instead of e to the negative r, I'll have e to the positive r. So I'll need a negative x to basically make it decay down. So this dotted bit is for negative x. So when I do this, every other contribution goes away except the real axis contribution. So from a complex x, again, I'm regenerating the real x that I had in the original inverse Fourier transform formula. But this itself, by the residue theorem, is 2 pi I times the sum of residues. The first only residue is at the pole I alpha. So I have 2 pi I, and then just evaluate this entire thing at I alpha. The denominator really goes away with e to the I alpha x. And again, as I said, this is for positive x. For negative x, there is no residue down there. There's no pole down there. So it's just going to be 0 by the Cauchy-Gursa theorem. Well, the top guy, this cancels out. This becomes a 1. Is e to the negative alpha x, and this is 0. So we've regenerated our f of x by basically using contour integration. We only changed the k from real to imaginary because we were working on the complex plane to use contour integration. In later bits, we will really have to fundamentally change what k or the frequency or omega mean. So we've regenerated what f of x is, and that's it. It works. This theory, it is really consistent. It really matches with what we started with initially, and so everything is just fine. It's perfect. It's a nice world here. The Fourier transform exists. The inverse, we've also found by some neat integration theory. It works. Everything checks out. Now my concern is, when does it not check out? So here's my concern. What do you mean by when it doesn't check out? Here's my concern. We had some alpha parameter here. I'm calling it a parameter because I'm going to set it to 0 now. So what if alpha went to 0? Which means this guy is just a 1. So our function of concern is 1 when x is positive and 0 everywhere else. What do we do with this? Well, we can try to take the Fourier transform of this. Let me just make the transform variable omega. Let me make this a function of t instead. Nothing really changes, because instead of k I have omega and instead of x I have t. It's fine. I'm just call that time, assuming we're working with signals here. So transform integral minus infinity bit is just 0, so I won't write that. We have 1. Well, let's try to integrate this. E to the negative I omega t. T is 0 and t is infinite. Well, now here's the problem. At 0 there's really no problem. This just becomes 1. At infinity, this e to the I omega t, this is actually cosine of omega t plus I sine omega t. So it does not really have a magnitude. This is just a phasor that is trapped in the unit circle of the complex plane, that's just going around with frequency omega. So if you take t as infinite, the argument inside is going to be infinite, and this guy is just going to keep rotating in this circle just really fast. So this really doesn't die out, it becomes undefined. Cosine of infinity, sine of infinity are both undefined. So there we have an issue. It's undefined on the upper bounds. So this really does not exist. Unless you have any other way of resolving this, it does not exist. But there is a way of resolving this. If we make omega complex, say omega is now complex. So here's how see, now I underlined it because it's complex. Our integration is going to look like this. E to the minus I omega t. Again, same evaluation here. Now since omega is complex, omega must have by definition a real part and an imaginary part, but it's multiplied with a negative I. So this argument is basically minus I omega real plus the minus and minus, the minus I and plus I become a 1 omega I. So now the new real part of this argument is the omega imaginary of the original bit. So the imaginary part will again keep oscillating like it's supposed to because of this formula. The real part, because if you split the exponential, this will become e to the omega I t. This guy can die down. And when does it die down? Well, we always want this to be a decaying function. This will be a decaying function when overall we'll have a negative sign. Since t is positive, we want omega I to be less than 0. So if we impose this condition into into whatever omega is, or the placement of omega, then on top this will just go to 0, and on bottom this is just 1. I'll have a minus from that evaluation, and that's it. This is essentially it. Yeah, I think I forgot a factor of omega somewhere. Yep, there should be omega here. My bad. There we go. That's the alleged Fourier transform, or should I say modified Fourier transform, because we've made the frequency a complex number. If you're thinking of signals, this might be a little counterintuitive. How can the frequency of a symbol of a wave be complex? But it has some properties in terms of optics, in terms of refractive index of, or how much the electric vector absorbs something. But again, let's not get too complicated. Since we have something like this, our contour integration is going to be interesting. So say we have a different contour now because we impose this condition that omega I has to be less than 0. So whatever contour we choose, we can't really be on the real axis because for two reasons. First, because of this condition we imposed, and even without this condition, notice what's happening. The pole is at 0, so the pole is here. It's here, right there. So if we put a contour here, like usual, we're gonna run the contour is gonna run through the pole. So there's gonna be a problem unless you do a Cauchy principal part where you sort of jump over or under it. But that's such a bad idea. Just let's just not do that. Let's just commonly agree to not do that. So, and again, we have this condition imposed as well. So, say if this is my pole, the imaginary part of whatever omega I choose, or the variable of integration, it has to be less than 0. So it should be here in the negative imaginary part of the axis. So say here's my contour, this dotted bit. So we're gonna run like this, some minus r plus some imaginary part. Sorry, here's minus imaginary or everywhere on this, and then just close on top when for positive time, and then close down for negative time because of this, basically the same arguments as before for the regular case. So here's what our contour looks like. Sorry if it's like messy, but hope you get the point. And we're integrating on this axis here. So if we invert, we're going to have, we expect f of t to be returned to us if the inversion works. So on this new contour, that's f prime d omega complex e to the I omega t f of omega complex. This is an entire contour integral which is equal to the integral on this lower segment here, on this lower segment, because the top part or the bottom part, depending on what contour you choose to do first, go to 0. So we have 1 over square root 2 pi on the top bar. This is say top, when the entire contour is the top. So we're just doing for positive t. And we have minus I over square root 2 pi omega complex. Now everything else is fine. And notice the residue here is whatever's inside. So what's inside the top contour is the residue at 0. So if we evaluate the residue at 0, you just have to plug 0 here in place of omega and we get 1. Everything else cancels out and we really have a 1 for t greater than 0 because we're working on the top contour. And for the bottom contour, if we close sort of on the bottom bit, well, here now there's no residue down there, so by Cauchy-Goursa this is 0, and this is for negative t, and it checks out. We really return, it really returns what we originally had for our f of t. So this theory of using a complex frequency really works. So a modified Fourier transform really works when we have some weird functions like 1 that really don't work with the conventional Fourier transform approach. So why not, let's just do this from the start. Why not just make omega imaginary or complex from the start. So from the start. So if we do that, then everything else is fine. We can define our modified Fourier transform as such. So I'm underlining because to denote omega is complex. And everything else is fine. We just need to care about what condition we impose, because that not only helps us put the contour properly, it also sort of tells us where there is a pole, because without this condition we could have really placed our contour on top. To avoid this line of the real line, we could have just placed our contour here in place of down there, but this condition sort of forces us to put it down there. Otherwise the Fourier transform, the forward transform would never really exist. So this having such an integrand would be out of the question to begin with. So I hope that sort of helps you. And then the inverse we defined in such a way, we have this, but we worked with the modified Fourier contour. I'm just writing this directly because this is equal to whatever you are integrating on. It's not really the real axis here anymore. You have to parameterize this as this. Say omega is negative r, or I mean those two are the points, so we have to parameterize this as such. Say some omega real minus I alpha. You have to parameterize it like this. That this is, you have to parameterize it like this on this bottom line, which is not really the real axis anymore. That's why I'm just writing it this way, so that whatever line you are on, which is not really the real axis, you can account for that based on this. So we can be a little more general about it. There we go. This is what the inversion should look like, and this is the modified Fourier transform. And now let's talk a little about the formalisms when we sort of move on to describe the Laplace transform. So here's the modified Fourier transform. Now what we're going to do is just sort of rewrite this to make our lives a little more convenient. So this I omega, I times the complex omega, I'm going to denote that as a complex S. And I'm going to collect all the square root 2 pi in the denominators. So that now let's just make it a function of S. So we have, say, capital F, which is complex, the function of complex S. We've collected these out and we're just going to put them for the inverse. So we don't have them here. Integral from 0 to infinity dt, it's still a function of t, e to the minus, just exchange st, we still have a function of t. Okay, this is a little modification to make your life more easier. F of t, now we've collected the 1 over square root 2 pi, so we have two of them, so we have 1 over 2 pi, and we are also going to write an I here because of this transformation. We need to account for the ds is I d omega. So we have this extra lingering factor of I from the differential, so we need to account for that. And now instead of a Fourier contour, I'm going to denote it as an L. I have ds e to the st f of s. And this is the Laplace transform pair. The infamous Laplace transform I've been referring to, and maybe you might have read about this somewhere, but this is the notorious Laplace transform pair. L is now Laplace contour. also called the Bromwich contour. So you can choose what you call it, but it's essentially the same thing. So say we've set I omega to S. What that does essentially, so we're working with an omega plane, and in our omega plane, our contour was like this. So this is your real axis. It was somewhere down or maybe on top. It depended on what condition we put on the omega imaginary. Right, what this was when we had the omega plane, the complex omega plane. Now what we do by sort of having this substitution in place is multiplying by I sort of rotates everything by 90 degrees in the complex plane. So now the S plane is going to look like this. So this is imaginary, this is real, this is your complex S plane. Since we've rotated everything, this line, because when we close like this or maybe below, the main line was important, is going to be rotated and it's going to look like this now. And we're going to be either closing from this way or that way, depending on what t, how t is defined. So this way for positive t, that way for negative t, and assuming hopefully there's some residue here or maybe on top somewhere, and then there's no residue here, so that we return our f of t. We have a 0 here because usually the Laplace transform functions are 0 for the negative region. So all that matters is the positive region here. So that's why we're hoping for no real poles or contributions to the contour integral from down here. And that's why this is pretty much consistent by how we close for a negative t. And I think this works as a good introduction to Laplace transforms, and I hope the motivation was sufficient here. One thing is, say we have the convergence condition or existence condition. Here it was, say, omega I is less than 0 for the one example. So for an f of t was 1 for positive. Here the real part of S is going to matter because look at, we're on the real axis, the contour is on the real axis, a constant real value. So in this case it's going to be, say, less than 0, which means you can place it here, you can place it anywhere, you can just shift it to infinity as long as it's less than, or in this case it's positive, my bad, sorry. So as long as it's positive, as long as you're not crossing or touching the imaginary axis or the real part of S is equal to 0 or negative, as long as you're in this positive realm here, the entire thing is going to exist. Your Fourier, your Laplace transform is going to exist. So you can really place it anywhere, and this is important because complex analysis, when we're trying to invert, there is a tendency of, or there is a strategy of sort of moving your contour around or deforming your contour deformation. And this really plays well with the region of convergence idea. So this is what we call the region of convergence. This is decided when we're doing the Laplace transform and we sort of want the integral to converge. So we force the real part of S to be greater than or less than. So if my f of t were, say, something like this, then I would have this, and then I would only care about the real part of S because alpha was always real, and I would force this to be positive. So this is the region of convergence imposed, that the real part of S has to be greater than negative alpha. So wherever negative alpha is, maybe here, there, doesn't matter, we just have to be a little bit ahead of it on the real axis because of this region of convergence. And we can be anywhere, it doesn't matter, because the closure is going to be a circle of infinite radius, so it will eventually encompass that residue point, that pole. So we don't really need to worry about it. I'll talk more about shifting this, and when the Laplace transform says that a Fourier transform is possible, that means when can we shift this? Because if we can shift this contour line to the imaginary axis, or when a real part is 0, that's where the Fourier transform exists, and that can be done. That's why Laplace transform is a little more general. We're in the complex plane now. So for Fourier transform exists when the real part of S is sort of like 0 is part of the region of convergence. And we will prove this. We will talk more about this. I hope you enjoyed the video. Please share in the comment section what you think, and stay tuned for the next one.